Today we're going to take a look at different types of chemical reactions. There are, I think I mistyped this, there are actually 5 types of chemical reactions that we are going to talk about. Synthesis or combination reactions, decomposition, single replacement, sometimes called single displacement, double replacement, also can be called double displacement, and combustion reactions. So looking at the synthesis first, a synthesis reaction is a combination. So often 2 elements, although it could be 2 small compounds, are going to come together to form one single product, a larger compound. So 2 individual reactants give you one product. If we looked at a general pattern, I've got element A, element B coming together to give me a compound of the 2. So here's a couple different examples what that could look like. Notice that subscripts or lack thereof here from my original reactants do not appear in the products. When I make my own products, I have to do my own crisscrossing. So when I have aluminum and oxygen come together, I would have to crisscross charges. Aluminum's got a +3 charge, oxygen has a -2. So when those crisscross down, that's where I get these subscripts from. So with that in mind, see if you can follow that same kind of process to predict the products for adding lithium and fluorine together. Remember, don't bring the subscripts with you. Just combine the elements and do your own crisscrossing. So take a moment and give it a shot. When you bring the lithium and the fluorine together, remember, none of these subscripts come with you, but lithium has a +1 charge, fluorine has a -1 charge, so all I needed was 1 of each. Now the entire equation isn't balanced. That would be a separate step that we could do afterwards. Here we're just looking at predicting what the product is. Our next type of reaction, a decomposition, is really the exact same thing in reverse. Here I have one reactant that's going to break apart to form more than one product. Often those products are individual elements or they can be smaller compounds. So here again is our general pattern. I have one compound as my reactant, and it splits apart to form the 2 elements separately. So it's the reverse of a synthesis reaction. Here's an example of what a complicated one could look like. I have calcium carbonate breaking apart to form 2 smaller compounds. Or, and this is more the type of example that you would have to be able to predict on your own. If I have mercury 2 oxide splitting apart, I'm going to get the individual mercury and the individual oxygen. Honkelbrief members, anything that has a that should be diatomic when it's alone, that you would have to watch for. When I'm asking you to predict products for things, I would only ask you to predict compounds that break up into separate elements. So diatomics would be the things to watch for. So with that in mind, your turn number 2, see if you can predict how that sodium nitride would split apart. Remember that the subscripts in your original reactant would never ever come with you. I'm just going to split the sodium and the nitrogen apart from each other. Sodium by itself can just be by itself. Nitrogen by itself is one of those 7 diatomics, so it does need to have the 2 here because nitrogen is diatomic. Balancing the equation again be a separate step afterwards. Third category are single replacement reactions. Here, one element is going to replace another in a compound. This can happen between metals or it can happen between nonmetals. So our generalized pattern, we've got an element and a compound switching places to give me a different element and a different compound. Here's the idea. If I've got a metal here by itself and then a metal and a nonmetal together in a compound, these 2 metals switched places so that this one is now by itself and this metal is now in the compound. So here's an example of what this could look like in a real equation. I've got sodium chloride and fluorine gas by itself. Here I have a nonmetal by itself, so it's going to switch places with the other nonmetal. The fluorine is now combined with the sodium, and the chlorine is now by itself. Anything that should be diatomic when it's alone, you would have to watch for in the products, and anything that you make a new compound, you would have to watch for the crisscrossing yourself. Sodium's a +1, fluorine's a -1, so the crisscrossing comes out okay on that one. And there's another example underneath it with aluminum oxide and calcium. Now I've got a metal as the one that's by itself, so it switches places with the metal. The aluminum is now alone, and the calcium is now with the oxygen. Again, keep in mind we do our own crisscrossing in the products. You don't bring subscripts with you. Calcium's a +2, oxygen's a -2, so that's why this one came out okay on its own. Always do your own crisscrossing from scratch when you make a new compound as a part of your products. So here's one for you to try. I've got aluminum and copper 2 nitrate. Following that single replacement pattern, see what you think your products would be. The element here that was by itself is a metal, aluminum. So that means it's going to switch places with the non-metal. It's going to switch places with the metal, which is the copper. So the copper will be alone, it gets kicked out. The aluminum will now be attached to the nitrate, and you do your own crisscrossing between the aluminum and the nitrate. Aluminum's a +3, nitrate's a -1, so that's where this 3 is coming from right here. Fourth type of reaction, double replacement reactions. Here I have 2 ionic compounds, and they're going to switch everything around, change their ions. This is where we get a precipitate forming. If you remember, precipitate was one of our 4 possible indicators of a chemical reaction, and this is the type of reaction where we're going to see them. So I've got 2 compounds to start with, and then I'm going to get 2 different compounds as a result. Here's our formula, or our generalized pattern. I've got A and B together, C and D together. Then they get rearranged. The 2 outside ions combine, that becomes one product, and the 2 inside ions combine. That's going to be my second product. You would always write the metal first and the non-metal second in each of these formulas. That's why this one on this side looks like it got rearranged. Another way you could think of this, it's kind of reminiscent of FOIL in algebra. If you remember trying to combine 2 things like this, it'd be first, inside, outside, last. Well, this is the inside and the first part of FOIL. If you have no idea what I'm saying, don't worry about it. Just keep in mind we're going to combine the 2 outside ions, that's one product. The 2 inside ions become the second product. So here's an example of what that would look like. I've got sodium and nitrate together. Silver and nitrate together, and then sodium and chloride together. The 2 outside ions are going to combine, the silver and the chlorine, so that becomes one product. I'm going to combine the 2 inside ions, which is the nitrate and the sodium. Those 2 together are my second product. Metal is always written first, non-metal second. That's why I switched the order in which they appeared. But the sodium and the nitrate get combined. I do my own crisscrossing in the products, but here everything had a charge of plus or minus 1, so everything came out crisscrossed okay. But that is something you would watch for when you're making your new products. Here's one for you to try. Predict our products here. Keep in mind the lead will keep the same charge that it has in the original reactant when you form it into the product. So give it a try, see what you can come up with. All right, we are going to combine the 2 outside ones, so the sodium and the acetate, that C2H3O2 polyatomic ion, that acetate will come together. Then the lead and the iodine, those 2 will come together. I can tell in my reactant here the lead has a +2 charge because acetate has a -1 and there were 2 of them. So I'm going to assume the lead will keep that +2 when I do my crisscrossing. Then here's the 2 products that I get. It doesn't matter if you write the sodium acetate first or the lead iodide first. It makes no difference. But you should have lead and then the iodine, +2 from the lead, -1 from the iodine, crisscrossed gives me the subscript here. And then for sodium, sodium's a +1 charge, acetate's a -1, so I just needed 1 of each for the crisscrossing there. Last category is combustion, and this one's the easiest. Combustion is a hydrocarbon, meaning any compound that has carbon and hydrogen in some ratio reacting with oxygen gas. This is burning. So I could have any type of subscript here, but it's C something, H something, plus oxygen gas is always going to give you these 2 products. Always, always carbon dioxide and water. So this is a very easy thing to predict. If you recognize you have combustion, CO2 and H2O are your products every time, no matter what. No crisscrossing, no switching, no rearranging, no breaking apart, no adding together, just CO2 and H2O. So if you recognize combustion, easiest one. All right, now let's see if we can put it all together. For this question, just look at the entire reaction, the whole thing is there, and see if you can decide which type, which of those 5 categories that reaction is. So take a moment and give it a shot. For the first one, hopefully you notice that you have 2 ionic compounds to start, and you've got 2 different rearranged ionic compounds to end. The 2 inner ones came together, the 2 outer ions came together, so that is an example of a double replacement reaction. For the next one, I have a hydrocarbon, carbon and hydrogen together, plus oxygen gas, giving me carbon dioxide and water. That is a combustion reaction. For the next one, I have an element by itself and then an ionic compound. The 2 metals switched places to give me a new ionic compound and a different metal by itself. That is what you see in a single replacement reaction. For this one, I have 2 elements that came together to form one compound as a product, and that's what we see in synthesis. And then this last one is the reverse of synthesis. I have 1 reactant which broke apart into smaller pieces, and that would be a decomposition reaction. Last one for you to try. If you can do this, you've got everything you need to. First, figure out what kind of reaction this is based on the reactants. Predict what the products are based on the pattern for that type of reaction, and balance the whole thing. Give it a try. First thing I might do is just write down what my parts are so I can see what I'm dealing with. I have plain old aluminum by itself added to lead 2 sulfate. So these are my 2 parts. Lead has a +2 charge based on that Roman numeral. Sulfate, the polyatomic ion, has a -2 charge. So these are my 2 reactants. Seeing this should tell you what type of reaction is. You've got a single replacement, an element, and an ionic compound. Knowing that it's single replacement now tells you what to do to predict the products. In single replacement, that single element is going to switch places with a similar element in the compound. So since my single element is a metal, aluminum, it's going to switch places with the metal in that compound, the lead. So the lead gets kicked out by itself, the aluminum is now attached to the sulfate, and then I just have to crisscross charges for that new aluminum sulfate. This would be what I end up with. I started off with aluminum alone and the lead to sulfate. When the aluminum and the lead switched places, aluminum is now with the sulfate, and I had to crisscross charges. The lead is now by itself. For the solid and aqueous part, anytime you've got a metal, it should be solid, and it says that it was a solution, so that's what tells you the aqueous piece. And then what you get as a result is another solution still dissolved, and the metal that's now a metal all alone would be the solid. As far as balancing, here you had to look at making sure you have the same number of each element on both sides. So since I had a 2 from the crisscrossing of aluminum sulfate, that is where the 2 here came from. In order to balance the sulfates, the SO4s, because I had 3 of them here, that made me put the 3 in this spot. And then the 3 leads, I had to put over here to balance the 3 leads. If you could work your way through this one, that is as hard as it's going to get. Very good job.